All right, so let's get started. My name is Iman Askiri. I'm a PhD student in the mechanical engineering department with Dr. Fang. My research kind of resonates with my colleague Ali Vaziri. We kind of work on using control theory, but using estimation to solve these kind of problems. Specifically today for my talk, I'll be talking about motion planning of autonomous vehicles using this approach of Bayesian inference. Okay. So first, a little bit of motivation. Why do we need autonomous vehicles? So there are great advantages that we can see if we use autonomous vehicles in our daily lives. The first one is saving lives, all right? The statistics on this is that I think in 2023, the statistics was that autonomous vehicles can save up to 12,000 lives in just the United States if everything is implemented well and we have full autonomy going on. The second most advantage is environmental factors. So the impact of carbon emissions coming from the tailpipes of diesel engines and gas vehicles can be reduced by up to 50%. So that's going to be much better for us in the long run for our next generation of children. All right. And commute time for us can be reduced by up to 18% in large urban areas. So these are the main advantages. But the question is, we're still not yet there, right? We still do not really see full autonomy, autonomous vehicles going around in our roads today. So why is that? This is because this problem of autonomous vehicles actually can be separated into few modules. The first one is about perception. Okay, the vehicle should be able to find out what's around it and be able to consider what is the decisions of other vehicles to get to that location that it wants to get to. The other one is how to get there, the motion plan. How do we get from point A to point B without having any kind of collisions and any kind of problems on the way? After we have that motion plan, then how do we execute that motion plan? That's the control part, okay? And after we have a controller, then we can apply it to the vehicle and get to our destination. For today's talk, I'm going to be concentrated on the motion planning problem. So what is the problem specifically? The requirement for a motion plan is that we would want a vehicle go from point A to point B. This trajectory along the points A and B should be safe and have no collisions. It should have some sort of optimality, meaning that we would want to use the least amount of fuel to get to that position, and we would want the passengers to be comfortable. That's some sort of optimality we're looking for. And we would want the motion planner that we are going to be designing to be as fast as possible, because real-time decision-making is actually what is going to allow us to get that safety that everyone is going to be comfortable riding these autonomous vehicles. So translating that, a motion planner needs to have three main characteristics. It should be able to avoid collisions. So we would need to have this constraint. We would need to have some optimality, and we would want to be doing this fast. Okay. So to satisfy two of these characteristics, which is optimality and constraint satisfaction, we use the framework of model predictive control. This is an optimization framework which considers a cost function. It also considers constraint, and it can solve these and ensure that the constraints are satisfied. So it utilizes a model of the vehicle that can predict into the future how the trajectory is going to look like, what are other vehicles going to be doing, and consider that within the constraint set and solve for the best motion plans. So it satisfies essentially two of them. We can get our optimality from it and our constraint satisfaction. And the predictive capability of the model is going to be able to have us look into the future and expect the unexpected, I would say. But the last point is still left, real-time decision-making. So here, we'll first look at the problem formulation of this. So we are interested in minimizing a cost function. The cost function for motion planning entails three elements. One is a reference tracking problem, where we would want to go from point A to point B. So how far we are from point B. We would want to minimize that distance. The control effort, that's the amount of fuel, essentially how much acceleration or steering input the vehicle needs. We would want to minimize that. And we would also want to minimize the discomfort of the passengers. So we do not want to be accelerating too fast or decelerating too much, or the steering should not be jerky. So the trajectory that we get is smooth. And this is subjected to the model dynamics. So we have a vehicle model, and we also want the safety constraints to be satisfied. So we do not want to have any kind of collisions happening. So this is, in general, the framework of model predictive control. Then a question arises is, how well can this work? Actually, it really depends on the accuracy of the model that we use. So many vehicle models have assumptions on the tire frictions. They consider it to be very like you have normal driving conditions. The assumptions are very simplistic, and it doesn't really grasp the complete dynamics, the diverse dynamics of a vehicle. So instead, we asked the question, how accurate can this really be for real world application? And to answer that, as I said, because of these assumptions, it might not be too accurate and it might not work too well in real world. So we're motivated to substitute it and go to a data-driven approach, where we use a neural network for the vehicle dynamics. And due to the abundance of data from vehicles, using different sensors, we have accelerometers, we have steering angles, all of the perception modules as well, can help us to construct a vehicle model based on a feed-forward neural network. Using this neural network, we then again embed it into this model predictive control framework, and we're interested in solving it for the optimal motion plan. But some of the challenges, as also Ali mentioned, for this kind of optimization problem, when we consider a neural network within it, we are faced with non-convexity challenges. That is, gradient-based methods can get stuck at local minimums and give us suboptimal solutions to this problem. And non-linearity of the neural networks also makes gradient-based method need a lot of iterations to converge to a point, if it doesn't actually get stuck at a non-feasible solution. And finally, because of those iterations, it'll be computationally expensive. So we had to come up with an idea, okay? To figure out how bad the problem is, we actually did a kind of case study. I created 3 different neural network structures with increasing complexity. The first one has 512 layers, neurons. This net2 has 2 layers, each 128 neurons, and net3, we have 4 layers of 64, 128, 128, and 64. And here we can see with the length of the prediction horizon of this model predictive control problem, the computation time of each of these networks drastically increases. So it's not really feasible to solve this model predictive control optimization problem using gradient-based approaches, because this is computation time up to 80 seconds, which is definitely not feasible for vehicle. So we had to, so then we can see here, so computation time increases with the complexity of the neural network. It scales poorly for large horizon lengths. And it would also fail actually if we go further than 40 steps of horizon length. So if we wanted longer horizon lengths, the optimization wouldn't even work. The scale of that optimization and the non-convexity is just too damning for gradient-based search. So then we try to come up with an idea and go away from gradient-based methods. And we instead, again, similarly formulate a Bayesian decision-making problem where we have some prior knowledge about what the trajectory should look like. And then based on the measurements or the desired reference that the vehicle should go to, which is the likelihood function, we try to infer the optimal solutions. So this could be represented as a conditional probability distributions where the state X is the motion plans and Y is the driving requirements. So we can essentially, for motion planning, we can write it as a conditional distribution where we are interested in the motion plans given the driving requirements, which is the reference, some optimality, minimum amount of fuel, and also collision avoidance. So these all go under these driving requirements. Okay? So the benefit of using this approach is that we can, using these Bayesian framework, we can handle the neural network's nonlinearity and non-convexity much more easily, and I can extend the length of the horizon to be much larger than what optimization methods can handle. So essentially, I worked on designing this framework for motion planning in a 2-way pass. It's first a filtering pass where we go from time k up to time k plus h, and then back to time k, considering all the measurements. But this would involve kind of 2 loops, a little bit computationally expensive still. But my recent work, by using augmented states, so I augment all of this from time k to t plus 1, and then k to k plus h, I'm able to do this in one pass. So this gives me, again, further computational advantage. So the single pass is much better than the two-way pass. And then the question is how to actually implement this distributions. We need to approximate these distributions. And this is done, again, by an ensemble method, where we consider a Gaussian distribution on our states x, where x is the trajectory the motion plan that we're interested to estimate, and y is all of the measurements, which are these driving requirements that we have for our autonomous vehicle. And these distributions are approximated using ensembles. So we have some, as I said, there's 3 stages. There's a prior, there's some likelihood, and then we get the posterior. So first, using the neural network, we would be doing a prediction step. So all of these samples are forward propagated using the neural network dynamics. And then we have to update that using the desired driving requirements using this measurement y to get the new ensemble or set of particles to approximate this Gaussian distributions. And with this forward pass, we can actually get much better efficiency, as we'll see in the results. So for the results, I first consider an overtaking scenario where the blue is the ego vehicle. It's the vehicle that's actually doing the motion planning. And we have the green and red vehicles to be obstacle vehicles. And we can see that here, I also have a simulation on this, so I'm not going to spend too much time on explaining this figure specifically. But in terms of constraints, this is the distance between the ego vehicle and the obstacle vehicles. We can see we set a safe distance of 1 meter. And we can see that the motion planner, this ensemble-based motion planner, is able to satisfy the constraints without problems. And this is kind of a simulation of how the ego vehicle moves and is able to compute the trajectory, the optimal trajectory here. And so we also did an experimental kind of simulation where we used real data. So the previous one, the neural network was trained based on synthetic data of a high fidelity model. But in this case, we consider a real world vehicle data where we consider a residual network design where the input of the network is the speed, and phi dot is the heading angle rate. And this is the actuation, it's the acceleration and steering angle. The neural network would learn the residual, that change in between 2 time steps from time t to t plus 1. That gets added to the previous state, and we can reconstruct the next state of our model. And the data is from a DevBot2 race vehicle. So that's TUM's race car. They have made the data available, and we have used that to train a neural network. To train this neural network. And here we have the testing of the neural network for both of these states. So the blue line is the true data, and the orange line, or the red-orange line, is the prediction of the neural network. So a pretty good fit using this residual network. And we also did an overtaking scenario with this. Everything looked good. So how about the computation? That's the main question that's remaining in terms of optimality and cost. So we compare it with a gradient-based optimizer, a horizon of 40. We see that that takes about 54 seconds. However, our algorithm with different sample sizes is orders of magnitude, about 99% faster for horizon of 40. And if you go to a horizon of 60, the optimization, the gradient-based method actually fails to get a solution even after 143 seconds. So we are able to achieve actually our goal of longer horizons and handling neural network dynamics in a much faster time. So in conclusion, so we have an MPC problem with a neural network that we consider for motion planning. We went away from the classical gradient-based method, and we proposed a Bayesian inference approach to solve this problem so that we solve it using ensemble methods, which are also parallelizable, as Ali mentioned, to get much faster or order of magnitude faster computations. Thank you. Any questions?
I have a question. So you tested on the scenario of overtaking. In other scenarios you have tested, or?
I have tested two other scenarios. One is an on-ramp merging scenario and also an emergency braking scenario. So both of those scenarios are I would say, yeah, easily within the computation time allowed for the algorithm. It solves the problem, no collisions, everything is satisfied within that framework as well.
And in the baselines you compare your method with, you show the neural network. That is also you design, or is it?
The design of the neural network is by me, and the training has been done by me as well. Yes.
Nice.
Okay. Thank you.
Just have one question. What was the trade-off that led to this huge amount of like time complexity reduction?
The trade-off, yes, good question. So why really we're able to get such great advantage in terms of computation is actually the breakdown of a large optimization problem into smaller sequential problems. So if I go quickly back to this kind of figure, this thing here. So the actual optimization problem would be considering all of the states from time k to k plus h. So the dimension of that optimization problem is much larger. However, here we can do it sequentially because of the Bayes rule that we use in the Bayesian framework, and this actually separates the problem into much smaller problems, breaks down the problem, and this is actually why we're able to solve it much faster than gradient-based optimizations.
Great, thank you.
Any question there?
Yeah, I was wondering if you considered like swarms of vehicles, or if all the data is really one.
That's a good question. So that's actually part of my future work that I'll be looking at, yeah, to consider other vehicles as well on the road running the same motion planner, and to see if we can consider communication between them to actually enhance the performance. Thanks for the comment. Yes.
Good question. What is the simulator you use?
The simulator that I use here for this final simulation is actually MATLAB's simulator. They have an autonomous vehicle toolbox, and so the scenario is set up in that, and the code also is written in MATLAB.
Like you showed us as a graphical.
Right. Yes, this rendering is done by this one. Yes, this is by MATLAB's autonomous vehicle toolbox.
And these scenarios, they already provide them.
No, I designed the scenario as well. So yes, you have the flexibility, like they have some preset road systems. Or you could also create your own road system. You can define your own pedestrians, you can define your own trucks, vehicles, different trajectories that they would take, almost anything. The possibilities are high, yeah.
Yeah, interesting.
Great. Thank you, Iman.
All right, thank you guys.